but I believe it is 1 p.m., so we're going to go ahead and get started. If you're in the right room, you're here to learn about functional programming and a little bit about domain modeling. So before we get into this, a really quick show of hands. How many people have actually done any functional programming before? All right, cool. Who just came into this talk because it sounded cool? All right, those are my real people. The first set, this is probably already passed, but that's okay. Cool, let's go and get started. So my name's Presley, and the first thing I want to mention is you do not need to take notes today. Everything you're going to see is already live. Slide deck, resources, code. If you trust me, you can scan the QR code. If you don't trust me, go to the URL, and you'll find everything you need to be successful. Momentary pause. And good. So here's what we're going to cover today. First and foremost, we're going to talk about Blackjack. Now, unless some of you are gamblers, maybe you're not familiar with all the rules of Blackjack, so we'll take a little bit of time. Once we've explained the rules, I'm going to show you how to not only identify those models, but design them in such a way that your fellow engineer can't break your code. Or if they do, they had to work really hard for it. And then finally, we'll talk about what happens when things don't always work out right. So with that, let's get to it. So, as a reminder for Blackjack, it's played with a standard deck of playing cards, right? So standard deck of 52 cards. And the goal is that you want to get the closest to 21 points without going over. And generally how this game is played is that you have one or more players, each of which is competing against the dealer. Making sense so far? Delightful. So here's how the game is set up. Each player is dealt 2 cards face up, and that forms something called their hand. And then the dealer is also dealt 2 cards, but only one of which is face up. So you don't really know what that second card is. And then once the cards have been dealt, a player, they get to make a choice. They can either draw a card to add to their hand, or they can stay and say, nah, I'm good, I don't want to draw any more cards. Once you make that choice, you keep doing this again until either you choose to not draw any more cards, or you go over 21 points, therefore busting. There's your technical term of the day. Once every player has taken their turn, the dealer then takes their turn. And then after the dealer completes their turn, every player compares their score with the dealer, and then whoever did the best wins. Cool, we've talked about that. Let's talk about scoring. It's based on a card's rank. And if you recall, aces can be worth 1 or 11 points. Face cards, that's your kings, queens, and jacks, are worth 10 points. And then number cards are worth that many. So 2s are worth 2 points, 4s are worth 4 points, so on and so forth. And if someone is dealt a hand with both an ace and some 10-point card, they have a blackjack. Anyone feel like this yet? Because I just went through like 6 rules of business, or 6 slides of business rules. Thank you. So let's actually break this down. So when I get this big nebulous problem, I actually use a technique that I learned from object-oriented, which is really identify the nouns. So for those of you who have an OO background, you may remember that nouns were your classes, verbs were your methods. Sound kind of familiar? So that's what we're going to do here. So if I take a look back at this original slide and I start identifying nouns, I start getting some of these options, right? We have things called a deck and a card, and then points are a thing, and then we have players, and we have a dealer. So all I'm going to do is I've highlighted these, and I'm going to put them in circles, right? We're going to make these just really nice little circles here with the names in them. And these will eventually turn into our full domain models. And let's keep going through the business context, right? So on this one, the only nouns that we had that we've not had before is hand. So we've got some domain concept called a hand. So we're going to add that to our chart of circles. And then on gameplay, our options are this choice thing or an action that they can take. So we're going to add that to the list. And then during the gameplay, the only real new noun that we get is this idea of a score. We had points before, but now we've got score. And so far, we've just got these happy little circles, right? We're going to Bob Ross our way through this. And then if we look through our scoring, there's a whole bunch of verbiage, but the only thing that you really care about here is rank. That there's some concept in cards known as a rank. So we've identified all these circles, but now we got to figure out how they relate to each other, right? Because it's pretty rare for a model to exist in isolation. It usually talks or deals with other things. So the trick I like to use is called has-a. And the idea is that if you can use the phrase has-a, then you know that they're related, or you need to put some reference there. Here's an example. So a game has one or more players, and a player has a hand, but a hand has one or more cards, and cards have a rank and suit. So do you see how that has-a, have-a kind of flows together? Well, once we do that, and we go through all of those circles, we end up with this really cool, funky-looking chart, right? For those playing along at home, you would know this is kind of like a dependency graph, right? Making sense so far? Kind of, we're seeing how they relate. Well, here's the trick. If you can draw it out like this, flip it upside down, and this will give you the way that we should implement. In fact, in certain languages, like F#, you actually do implement things in a front-down or top-down fashion. But enough about this. Let's start talking about the modeling. Now, I don't know about you, but I like writing code that works. How about you? Right? For those of you who work in a statically typed language, you probably like catching your errors at compile time and not at runtime, right? Cool. Well, that's how we're going to design our code. We're going to design our code in such a way that you can't ship bugs, because if you did, the code wouldn't have compiled. Like, that's how we're going to catch that stuff. And the reason why is that Jeff Atwood has this really great blog post called Falling into the Pit of Success, where he says that a well-designed system makes it easy to do the right things and annoying, but not quite impossible, to do the wrong things. Another way of thinking about this is that I want wrong code to look wrong, so it shows up in PRs wrong, so it shows up in those code reviews and everything else. So let's start implementing. So when we look at a rank can only be one of 13 values. And if you're wondering why I use the term rank, that's because that's the actual domain term for that in a card. The cool thing to remember about this is that if you're ever modeling a type where it can only be one of a set number of things, you can use a concept known as a sum type. So in this case, I'm using a language called TypeScript to help me out. But if you're working in any other functional language, they'll have something called a discriminated union, sum types, tagged unions, so on and so forth. But in this case, we've defined rank to either be the strings ace, jack, queen, or king, or the numbers 2 through 10. So just by making this one small change, I've already prevented errors from happening like this, where if I try to define rank and give it the string kumquats, it won't compile, because kumquats is not a type of rank. So this is already a big win over enums, for those of you coming from an OO language, because you could always typecast a number into an enum. And this definitely helps us avoid stringly type systems, which have their own set of problems. But yeah, so that's rank modeled. Let's tackle suit. So a suit can only be one of 4 possible values as well, right? Hearts, clubs, spades, and diamonds. Since it can only be one of 4 possible things, it can also be a sum type, like so. And same thing as before, right? If I tried to assign this as a bad string or something, it won't compile. So we've got rank and suit defined. Let's take a look at card. Now, card is different because it has things. You can't say it's only one of a type of rank or one of a type of suit. It has to model all possible combinations. When you run into this, this is known as a product type. Now, in TypeScript, I'm using the type keyword to come up with essentially a record, but depending on your language of choice, it may be called other things. So in this case, card can represent any combination of rank and suit. So much so, in fact, that if I try to define card and only specify the rank, TypeScript won't let me do it because it says, hey, wait a minute, you never set suit. This isn't a valid card. So once again, I'm already removing a whole set of errors that my engineers could get into just by defining my types like this. A question I get a lot of the time is, how do I keep some types and product types separate? The key word is or. If you have a type that can only be one of a thing, it's or, it's a sum type. On the other hand, if it has to represent a combination of values, or you can use the word and, you've got a product type. All right, we've got rank, suit, and card defined. Let's go take a look at a deck. So a deck is pretty much what it sounds like on the 10. It represents one or more cards. In this case, we can use a type alias. So in our case, we're going to say type deck is any list of cards. You give me an array of cards, it's valid. Easy. We're going to do the same thing for hand. Hand can also be one or more cards, and so we're going to use that same type alias trick where we say hand equals card. This is going to get really interesting because now we've said that deck and hand are both arrays of cards, which means we can do fun stuff like this. So let's say we have a function called draw that you pass in a deck, it'll do some stuff. Well, I can create a hand like so, and then I can call draw with it. Do you think there might be a problem of allowing someone to draw cards from someone else's hand versus the deck? Do you think that could be problematic? Yes, depends on the game. But let's say that my neighbor has that ace that I really need. Probably don't want to let them be able to do that, right? Well, unfortunately, as of the way we've defined all of these things right now, that's valid code. So let me show you how you can fix it. Now, it's called different things in different languages, but in this case, it's literally called a single case sum type or a tagged union. So I'm saying deck is some record where it has a property called tag, a value deck, and then it also has a value property that is that card array. Now, the minute I do this, deck and hand aren't the same anymore, which means I can't pass them. They're not interchangeable. So if I do the same code from before, but now that I've updated deck, I get this really helpful error that says, hey, wait a minute, hand's not assignable to type deck, card list or card arrays missing all this other stuff. So this is a small but subtle way that I can prevent my engineer from accidentally allowing someone to draw cards from someone else's hand. So with hand defined, we can now take a look at player. Now, player only has two things. It has an ID and it has a hand. So we're going to use the product type like we did before. And now we're reusing those types, right? Hands of type hand, this will work no problem. Dealer's even simpler because there's only one dealer, right? So it just has a hand property. So it's also going to be a product type. So far, so good. Last but not least, we can finally model the game type. And if you're playing a game of Blackjack, you're going to need some players, a dealer, and the deck. So that's going to be another product type, defined as such. And just like that, we've already modeled the big chunk of the Blackjack, but we haven't gotten into some of the fun parts yet. So let's take a look. So points is an interesting domain concept because it can be one of two different shapes. Some cards, like kings, queens, jacks, and sevens, they're only worth one value. The aces are worth two different values, either 1 or 11. So we're actually going to take some types and product types to make this type for points. So first, I'm going to define a type called hard. And if you're wondering why it's called hard, it's because it's one of those other domain terminologies for Blackjack. So I give it a tag called hard and a value of a number because if I have a hard point, then it can only have one value. Soft, tag a soft, but its value is actually going to be a tuple, two numbers, because it could be 1 or 11, and that's for the aces. And now I've defined hard and soft, I can say points is either hard or it's a soft. This is a really slick way of taking your smaller types and combining them into more clever types. So points defined that way, we can model action. I can go ahead and warn you, the game of blackjack has all sorts of crazy things you can do. You can double down, you can split, you can do all sorts of crazy stuff, but if we modeled all of that, we'd be here all day. So we're going to make this really simple. We're going to let you do one of two things. You can either hit or you can stay. There's that or word again. That means it's a sum type, so we can model it like this. Hit or stay. Last but not least is score. So someone's score in blackjack can only be one of three things. Either you got a blackjack, congrats. So in that case, we have type blackjack and just has that tag. No other data because we don't need it. If you've got a blackjack, you've got a blackjack, that's sufficient. If you didn't get a blackjack, you could have busted, right? And if you recall, this is what happens when you go over 21 points. And if that happens, we want to know how much did you bust by. So we're going to store that in value, just like so. And then last but not least, you could have also stayed. So maybe you got like a 19 that you're wanting to hold on to. So we're going to model it. Now, even though busted and stayed are containing numbers, that tag is how we know whether it was a busted or a stayed. And now once we've defined those three things, we can say your score is either you got a blackjack, you busted, or you stayed. Making sense so far? Okay. So we've modeled everything. Here comes the fun part of today's presentation. Here's the entire problem domain for blackjack on one slide. Yeah, now granted, I've had to like one line some things that maybe could have been multiple lines, but that is everything you need to actually start implementing business rules. I don't know many languages that are still terse and clear enough that I can model it this way. Also, I'll ask the question, do I have any non-engineers in the room? Yeah, so the fun thing you can do is show this to like your product owner, explain that the single bars mean or, and they'll be able to follow along. They'll actually be able to read this pretty well, which I think is also kind of cool. So we've done the models. Let's get into playing blackjack a little bit. And more specifically, let's talk about scoring a hand. So I'm going to ask the audience, which is a terrible idea, but I trust you all. You've been with me for so long. So let's say that we wanted to figure out the score in someone's hand. So we got to add up all the points. How would you do that? You don't need to give me code. You can just give me like a rough algorithm, pseudocode, whatever. But if you had to sum up a list of numbers, what would you do? I've not worked with that individual, but yes, right? We're going to convert each card to how many points it's worth, and then we're going to add them up. So let's do that. So as a reminder, here's how we defined points before. So let's go ahead and write that first step, card to points. So I've got a function that says if you give me a card, I'm going to return you points, and I'm going to do a switch on its rank. Now, if it's an ace, I'm going to return back that soft value. Because remember, aces could be worth one of two values. Jacks are worth 10, queens are worth 10, kings are worth 10, and if it's something else that's not one of those four, it's a number, so we can just return that back. For those of you playing along at home, you may recall this is exactly how I defined points like 20 slides ago. Not too bad. In fact, this is pretty easy to unit test if you wanted to. So now we've converted each of the cards to points, but now we got to add them. Now, unfortunately, points aren't just numbers. There's some other stuff that has to happen. So if I just write the general function shape, I know it's a function that takes in two sets of points. It returns points, which means I got to handle all four permutations. If both the points are hard values, if one of them is hard, the other one's soft, and then if both of them are soft. So instead of writing all of this in one slide, let's start writing these as smaller functions. So if we're adding two hard values together, it'd be like if I had a hand of 4 and a 7. So in that case, it's pretty straightforward. We're just going to take those two values and add them together. And if you have two hard values, it's always going to be a hard return. So in this case, we would get like a hard value of 11. okay? Now, if we're adding a hard and soft value together, that'd be like adding an ace and a 5. So it's going to be a little bit trickier. But what we're going to do is we're going to take that tuple, deconstruct it into a low and a high value, and then we're just going to add that 5 to the low and high. But if you ever add a hard to a soft, it's going to be a soft value. Once again, and hopefully you're seeing that these functions would be pretty easy unit test. Nothing too terribly complicated here. Also, if you're adding a soft and a hard, it's going to be the exact same function. You just flip the inputs. So there's no slide for that. But our last one, what if you're adding two soft values together? Maybe you got really lucky or unlucky and got dealt two aces. Here's what that would look like. Now, it turns out that you can always throw out one of the high values because if you add the two high values together, it will always be invalid, so you can skip that. But we'll deconstruct A into a low, throw out the high. B will be the B low and B high, and then we'll add those values together. Once we have this function defined, we've got to do one last step. And this is where we have a situation where a soft score isn't valid. So let's say that you had in your hand an ace and a 9, which is already a soft 10 or a 20, but you were dumb and decided to draw a card anyway. What are you doing? And then you get hit with like a 10. Okay, now your score is a soft 20, 30, but 30, you would have busted with that, right? So you're no longer in that soft scenario. You have to go to hard, so it'd be a hard 20. So we've got to write a function to do that. We'll call it normalize. And it's not too bad. Essentially what we do is say, hey, if the point, if it's a soft, and its second part of the tuple is more than 21, congratulations, it's now a hard value. Otherwise, return what you passed in. It's good to work with. And once we do that, our add points function from before looks a lot like this, where depending on what tags the points were, we call the right function and we normalize everything. Not too bad. So as someone mentioned earlier, card has to go to points and we got to figure out a way to add them. So now let's score a hand. So here's hand. You give us a hand, we'll give you some points. Our initial value is going to be a hard value of 0. So this essentially would be like what happens if you didn't have any cards in your hand. You have 0 points, right? Then we iterate through the hand, and for each card, we call a card to points, and then we update the total and say, hey, total equals whatever add points is. And then we return the total. If you were to squint your eyes and replace add points with just regular addition, this is your standard running total loop that you've all written like 20 million times by now, right? Let's make this a little bit more functional. So score hand works, it'll totally be fine, but we're using TypeScript, so let's do some other fun stuff. So instead of doing the for loop, we can instead say, hey, our initial points is that 0, and then for hand, we're going to map each of the cards to points, and then we're going to use reduce to reduce down those list of points using the add points function. A little bit cleaner, a little bit nicer. You're not having to deal with temp variables. Pretty slick. So we've scored a hand, but let's get into something that's a little bit more interesting, drawing a card. So we have this function called draw that says, if you give me a deck, I'm going to give you back a new object or a new record where here's the card that you drew and here's the rest of the deck. And we can deconstruct the deck like so, where we say, all right, card's the first element, rest of the deck is rest of the deck. And then we're going to return back the card you've drawn and the rest of the deck to draw from. And this works. In fact, here's an example of us trying to draw a card from a deck with multiple cards in it. And you'll see that the result is the card that we drew was an ace of hearts, and the remainder of the deck is 7 of spades. Works no problem. What happens if the deck is empty? Oops, undefined. I don't remember our function adding points know what to do if a card was undefined. Do you? Nah, it's not great. So we can, and unfortunately TypeScript out of the box wouldn't have warned us about this. It would have happily given us undefined, and you would have only caught it runtime. That sucks. So let's fix that. So the issue is that we need to let the caller know that when you draw a card, it could fail. It may not have anything. So one way we could do that is update the signature to say like, hey, it could return back a whole object, or it can return back undefined. And then we put this error handling logic that says, hey, if I don't have any length in that list of cards, return undefined. Once we make this change, and we try to draw an empty deck, we get undefined, which is great. That means it failed. And TypeScript will help us out, because now when we call draw, it'll say, hey, wait a minute, this could be null. Don't believe me? Let's take a look. So let's say we need to draw multiple cards. Here's a function called draw 3 cards, and it's going to do exactly what it sounds like. You're going to get 3 cards. So the first thing we do is we call draw with deck, and then we check to see if we got a result back. If we didn't, we bail. We try to draw a second time. If that doesn't work, we bail. We draw a third time. If that doesn't work, we bail. Otherwise, all 3 of our draws succeeded, so we can return back the data that we need to. There's something a little bit rough about this code, though. We use that pattern a lot, right? Where we do a thing, if check it, bail if it's not good. Right? So we're better in the fact that we're being more explicit with our types, but the problem is that we've kind of got this repetition going on. Now, for those of you with a Go background, this feels right at home, right? That's how Go does their error handling. But let's take a look at a different way of handling this. So the problem is that we need a way to model a type that has 2 shapes. Either we have a value or we don't. There's that or word again. What's a type that we've learned about this afternoon that uses or? Some types. So let's write our own. In a lot of languages, this is called option. In other languages, it's called maybe. But this is like your first functional programming pattern, using maybe or option to handle a missing value. So I want to use the maybe syntax of just and nothing. So one of our types is called just. It has a tag of just, and it'll have a value of whatever it is. It's a generic, so it'll hold up just fine. And nothing is exactly what it sounds like. It's nothing. So our maybe then is either you have just or you have nothing. For those of you with a Rust background, this would be the same thing as saying, oh shoot, I just totally forgot what it was. Some and none. There we go. Similar concept. The just nothing comes from Haskell. With just those types, we can write functions to work around it, but I'll go ahead and warn you, it can get a little bit messy to read. So you don't really run across that a whole ton. Instead, you get something called like an expression, or you get like a result builder, something like that. That's a lot of code there. I'm not going to ask you to read all that. Let's break this down. So the first part of the class is we have a private constructor that's going to hold on to the maybe. And it gives you 2 static constructor methods you can use. Nothing and just, which does exactly what you think they do. They'll either give you back a nothing or a just. With those in mind, we can define something called map. Now, what map does is it says, if you give me a function that can convert from one type to another, I'll give you a new maybe. So if the maybe that we already had was nothing, you get nothing back. There's no work to do, right? There's nothing to convert. But if we do have a value, then we're going to give you back a new maybe. Except it's a new maybe of just, and we're going to go ahead and convert that value over for you. So map is great if you always know that what you're converting will always work. For those of you with a .NET background, this is essentially select on a list. Similar concept. Bind is a little bit more interesting, because what bind tells us is that if you give me a function that can take a value and returns back a different maybe, then you'll either get nothing if I had nothing to do, or you're just going to get back that new maybe. This is great for when the operation you're trying to call could fail, like maybe drawing a card. So let's take a little bit of a closer look at what that would look like. So here's a new function called maybe draw. It's the same layout semantics as the original draw, The big difference, though, is that instead of returning back an object or undefined, you're getting back this maybe expression. And instead of returning undefined if we don't have a deck, you're getting back nothing, right? Because if you can't draw, you're going to get nothing to work with. And then if we were able to draw, you get your just, right? Hey, you get your success. Here's what that maybe draw 3 cards looks like now. So same inputs, but here's how to read it. We're going to try to draw from the deck. And if that works, we're going to try to draw a second time. And if that works, we're going to try to draw a third time. And if that works, we're going to convert those 3 draws we've had into be for that shape of cards and for the rest of the deck. And y'all got your first design pattern using the option and maybes. So we've covered a lot this afternoon, a lot of cool new concepts, a lot of new error handling. So I just want to take a few seconds to kind of recap all of the cool concepts. The first one that maybe was new for some of you is this ability to use nouns to identify our domain models, right? Because once we started using nouns, that kind of gave us an idea of what related to what and how they fit. You also hopefully learned about some of the cool, powerful things that you could do with sum types and product types, and how you can be really powerful on your constraints of what developers can do and what they shouldn't be able to do. And then finally, you got to see how do we handle missing values using the maybe pattern or the option pattern. With that, I just want to say thank you so much for letting me come out to Star Trek this afternoon. I had a blast. Once again, that is the QR code for slides and resources if you need it. If you've got questions and you're not really sure, like you want to talk to me about it, you can always send me an email. I know in the Discord for Star Trek, we have like the forums near the bottom. You've got those options as well. So thank you so very much. Last thing I will mention. Let's say that you saw this talk and you're like, ooh, this is really interesting, but I need more hands-on stuff. I have a Udemy course coming out in the summer of 2025 where we will build all of this from scratch. I'm talking file new to a working version. If you want to know when this comes out, just scan the QR code. I swear it's just an email. That just lets me know that you're interested. Thanks, y'all. I appreciate it.